Hi, everyone. So it's just about 9 a.m. So I'm going to begin with this review. We'll start with a few, we'll be covering these three topics: the active passive sign convention, voltage, current dividers, and Thevenin and Norton equivalents in that order. So we'll start with passive sign convention. That's what's used most often. So that's where I'm deciding to begin with. The purpose of this, just sign conventions in general, is really establishing a relation between your voltage and current in the circuit. And passive sign convention is one of the two ways we are going to represent that. And the reason we have passive or active is just because they need to be uniform and consistent. So you need to choose one of the two. Passive sign convention is written like this, any form that's like this. So these three are, we have a resistor, capacitor, inductor. It doesn't change much of what's happening. So if we take a look at the resistor, we have our current IR, and we have our voltage polarity with the positive on the top and negative on the bottom. So this is passive sign convention, as the current IR is going to flow into the top, the positive, and come out the negative of these voltage polarities. And this will be the same for our capacitor and for the inductor. Now, this could be written upside down or left to right, right to left. You just, or diagonally, Y delta, you need to really look for the current is going into which side of the sought voltage. Okay. So we can go to this example. I'll give it one second, and then I'll continue on. So here we can see it looks almost exactly like the previous slide. So our IR, our current through the resistor, is going to be positive. And that's because it's going into the positive, out the negative. So we're going to have IR equals, we need a voltage over a resistance, Ohm's law. So we'll have VR over R is 10 volts over 5 kilo ohms, which should be 2 milliamps. Positive. Awesome. So consider A and consider B. Now for these two, we don't necessarily need to solve for the current, because we're more worried right now about whether it's active or passive. So I would take a look at this. Let's take a look at A. So A is one of those variants of the passive sign convention I talked about at the beginning. Is you could do it up, down, left, right, diagonally. So this current IR, I wrote it twice just so you might be able to see it. I wrote it here, and I also wrote it here. And it goes through the same direction, doesn't change. It's going into the positive. So this current IR would be a positive 10 volts over 5 kilo ohms, same 2 milliamp answer. Now consider B. B is different. B, the current IR, is going into the negative terminal, coming out of the positive. So in passive sign convention, this would actually be IR here would actually be a -2 milliamps. Active sign convention is basically considered the dual of passive sign convention. So anything that would be negative in passive would be positive in active. Anything that would be positive in passive would be negative in active, and vice versa. And looking at the third bullet point, we can see that the current entering the negative terminal, exiting the positive, so a voltage rise would be considered positive. Whereas, as I've just mentioned, that a voltage rise in passive sign convention would be negative. So looking at this one, you can zoom in a little bit. What would this one be in active sign convention? I even wrote it here. I'll give you 1 second. And this is IR. You could adjust it. It could be any current. So looking at this in active sign convention, we have negative to positive over the resistor. That is a voltage rise, right? We start low and then we build high, we rise. So there's going to be a voltage rise in active sign convention would be positive. So this would simply be IR would equal 4 volts over 8 kilo ohms, which is going to be 0.5 milliamps. Positive. Now, if this were passive sign convention, this would be negative. And it will work like that. So whatever we have in passive would be negative in active. One of the main tips and main things you need to keep in mind is that you must stick with it. It must be uniform, must be conform, because if we do half of the circuit in active sign convention and then the other half in passive, then it's all messed up. It's gonna lead to way different answers. So some of my tips with sign conventions and getting started with it is when you begin analyzing a circuit, you need to decide which sign convention you want to use. Now, how do you decide which sign convention? Now we can go to our third point. We can skip the second one for a minute. Passive sign convention is used most frequently in many of the circuits that we've solved. We do. We tend to use passive sign convention, but there are some cases where active may be more beneficial, and that's definitely when we're working with power absorbed, power supplied, in this case absorbed for active. And now this is a very main point. I've kind of already underlined it. After you choose which sign convention you're going to use, you must stick with it. You have to stick with that sign convention unless you restart. If you want to change it, you need to restart. You need to redo it all, or change all the signs. But I would stick with choosing passive or active, and then finish analyzing that circuit with that sign convention. Now, this is a little just analogy I kind of make with passive active is like considering a plate of cookies. I would say passive, we use it more, so I say it's more the positive of the two. So it's the more optimistic one. So if you consider a plate of cookies, and this is in regards to power, when I supply a plate of cookies, so I want to give you 2 cookies, passive sign convention would look at this in a happy way. They are positive because they are very happy that you're receiving the cookies. On the other hand, active, they're in the power supplied, they're the more pessimistic of the two. So rather than being happy for you, they are sad that they're the ones losing the cookies. So power supplied, passive's happy, and active would be sad. And then this would be vice versa for absorbed. Absorbed cookies, the active sign convention is a little more greedy of the two and really happy he received cookies or they received cookies. And passive would be the opposite. They would be sad that, oh no, you should keep your cookies. And that kind of helped me when I was first figuring it out. So now we'll move into the next topic, which are voltage dividers. So that ends the active passive sign convention. So voltage dividers are one of the most fundamental circuit combinations that we're going to evaluate. And it's one of the very first ones we went over. Most of the time, we want to simplify our circuits into these voltage current dividers. We've already learned nodal mesh analysis, superposition. We would really like to be able to solve these rather than using any of those other methods. If you remember, nodal mesh analysis is one of the last things that we want to do. So considering this circuit here, this is going to be just a plain voltage divider. We have a voltage source of VI in series with two resistances, R1 and R2. So in this circuit, this voltage divider, we can get a voltage across resistor R1. We could get we could get one across R2. We could get one across VI, but if we got one across VI, it would just be VI. So, same problem. We'll have this example. We want our sought voltage over the 5 kilo ohm resistor. So I'll give you a second. See if you can write out that equation and solve it. So we'll get started here. So we have a voltage divider. So our load resistance, the voltage we want, the resistor where we want the voltage over is going to be the 5 kilo ohm resistor. So in a voltage divider, this one is going to be the numerator. So we take our V out, our sought voltage V out is going to be 5 volts. Now, this is another thing relating back to sign conventions is that 5 volts going to be positive or is it going to be negative? In this case, it's going to be positive because the positive polarity of our sought voltage aligns with this source. The positive here, it touches the positive here. So they're both, it's going to be a positive 5 volts. And then we have our sought, we have our resistance there, and then we have the sum of the two. This gives us 5 over 15, 1/3 times 5, about 1.67 volts. Be volts, kilovolts. No, it'll be kilo. There we are. I may be wrong. I don't have a calculator. Let me grab one here. Yep, 1.67 kilovolts. Awesome. So, a quick thing here. What would happen if rather than that being the positive, that we do a negative and a positive here? that would just change this to a negative 5 volts. And we would have negative 1.67 kilovolts. Awesome. So this is a little addition into by me, because I know if I saw this at the time, I would have freaked out. I would have had absolutely no clue. This is a voltage divider. It's very close to exactly what we just looked at, except the resistance 1 is on the top, where it would be, if that were the same, it would be up here. But you'll see these a lot, especially when you get into operational amplifiers. These come out a lot. So the best way to look at this, and we want our voltage across the load resistance of R2. You could, in my head, I sometimes draw a connection here and then add my ground, just so now it looks exactly like that series circuit we would have seen before. But sometimes you'll just see it with going the black lines. And I just wanted to make sure you could see that and see how that is a voltage divider. So now we'll get into current dividers, which are similar to active passive. This is the dual of the voltage divider, current and voltage. These show how current's divided among parallel resistors. So if you remember, voltage divides across series resistances. Current will divide across parallel resistances, and that brings back the idea of duality. So here we have this circuit. We have a current source and 2 resistors in parallel. So if we wanted, we could either find I1 here, or we could find I2. What we're going to do is we're going to write 2 equations for these. Now, the difference with a large difference here between this and voltage dividers is our sought voltage in a voltage divider. That resistance is the one that is in the numerator. For a current divider, that's the opposite. So if we wanted I1, the resistor that's going to be in the numerator of our, when we divide, it is going to be R2. And this is for a reason, a couple of reasons. Main reason is that if you've ever heard, current takes the path of least resistance. This is one of the larger reasons of why this happens. So let's consider I1 and I2. Now we can look at the current IS. IS, if you think, is going to keep flowing up this way. So now we'll know I1, I2. They're both going to be positive. Okay. So if we're writing I1, this is going to be IS. Both of these are going to start with IS. And we can write these next to each other. We'll solve I2 as well. So this current source. And then for I1, like I said, think about which resistor is going to be in the numerator. I1 goes through R1. So actually, it's going to be the opposite. R2 is the numerator. And for I2, the opposite as well, R1. And then we can add the 2 parallel resistances. And this solves for I1 and I2. So let's look at this case. And this case is similar to this one. Here, I will draw a line here. Add a current source, IS. And we really don't need this. So we have our current going, we go like that, there. So what would the current I2 be in this case? And think back to what I said about why R2 is in the numerator here, right? And when I explain, I'll say that phrase again. So what's the current I2? So I2 in this case is going to be 0 amps. Now, why is it 0 amps? Think back to that phrase oh, my bad. I said at the beginning, path of least resistance. Current takes a path of least resistance. So if I1 here has no resistance, that's less than R1, whatever R1 could be. So no current, all the current is going to go through I1. I1 is going to get all of IS. Therefore, I2 will be 0 amps. So now we get to the last topic, starting here, is we have our Thevenin and Norton equivalents. So we'll begin with Thevenin. The Thevenin's theorem states the behavior of any linear circuit. Now it's in bold, linear is important. And we don't need to go over nonlinear. All we've looked at are linear so far. Linear circuits are resistors, capacitors, inductors, current, voltage sources, all of what we've dealt with, dependent sources. Any linear circuit at a specific pair of terminals may be modeled by a voltage source in series with an equivalent resistance. And we can see that here. We have our linear circuit, and on the right, we modeled it with a voltage source and a series resistance. So that would be our Thevenin equivalent. So no, this model does not mean, so these are two notes I want to say. This model does not mean the network is just a voltage source and a series resistance. That it's just a model is exactly what it is. It's a second-hand drawing of the network. The network's still there. The network's still a bunch of different things, but we're modeling it with a voltage and a resistor. And number two is the circuit must be linear. So next we have a Norton equivalent. And Norton equivalent, like active passive or voltage current, or parallel series, Norton equivalent is the dual of the Thevenin equivalent. So, and you'll see the definition is very similar. The theorem states that the behavior of any linear circuit at a specific pair of terminals may be modeled by a current source in parallel with a resistor. And now we'll see the same exact, that linear circuit didn't change, but this one did. So now we have our current source and our parallel resistance. So this brings up two questions. If we had a Thevenin equivalent, does this mean we can derive a Norton equivalent from it? Yes, we can, because we know V open circuit is equal to I short circuit times R Thevenin. So if we know two of these, we know the last one. And we know ISC RTH, we know VOC. If we know VOC RTH, we know ISC. If we know VOC ISC, we know RTH. And one way, so if we find VOC ISC, we can easily find RTH. But what if we're trying to find RTH and we don't have either of those two? We would deactivate all of the dependent sources in the circuit, and we would find the equivalent resistance from the output terminals. And now the output terminals would just be A and B here, where we're trying to look into that circuit network, that linear circuit. So consider this example, and we're going to try to draw both the Thevenin and Norton equivalent. So the first thing that I would do here is, well, you can do a couple of things. The first thing I see is that we can actually do a source transformation. As you see, the 8-volt voltage source is in series with that 3-ohm resistor. So remember source transformations, the current is going to be the voltage over the resistance. So let's redraw this. We have our 8-ohm. We have our 2-ohm, sorry. That didn't go anywhere. And now I will take a second. We can't get rid of anything here, so all that stays. Now we have a parallel resistor of 3 ohms and our current source. Now think of what this current source is going to be. Polarity wise, my bad. It's going to be the same as that voltage source, or we're kind of looking where that positive of that voltage source is going to be the head of our current arrow, or the direction. So it did move over a little bit, right? It was up here and now it's moving down here. It's still going to be pointing upwards. And now there are a few things we can add here. Let's look. We have a 2 and 3 ohms, so we can combine those in parallel, which is going to be 2 ohms, 3 ohms over 5 ohms, 6/5 ohms. And then that we can just do another SOT variable transformation from there. And I'll draw that out so we can see it. We have that. And now we can do a SOT variable transformation. We have a current source in parallel with the resistance. We can get a equivalent voltage source, and then we'll be left with something very close to our final product. I'm going to put the resistor on the top. You could put it on the bottom, as long as it's in series. And the voltage here is going to be 6/5 times 8/3. So we're getting some weird numbers, and I am keeping them in fractions. But you could do decimals just as long as they're equivalent. And now these two resistances are in series, so they can just add. And make sure we keep I and V out. My bad. So those two adding, we will be left with which equivalent circuit? It's one of the two, Dividers and Norton. You're thinking this is our Thevenin equivalent. We have a voltage source in series with an equivalent resistance. So our V open circuit is going to be 48 over 15 volts. And our R Thevenin is going to be 46 over 5 ohms. Now, we can find our ISC from this. ISC equals VOC over RTH. Which in this case is going to give us 1 second. Eight over 23 amps. My bad. 8 over 23 amps. Just making sure that's right. Yep. And from there, we can draw our Norton equivalent, which I will get rid of this guy at the top. We could draw our Norton equivalent so we know ISC. Keeping voltage still stays there. Everything. So we have our resistance and our current source. Pay attention to which way the voltage is here. Our current source is going to be arrow towards the positive. We know RTH 46 over 5 ohms. And ISC is 8 over 23 amps. And this would be our Norton equivalent. And the bottom would be our Thevenin equivalent. One last thing is going back to one of my points back here is you could this point right here. So we turn off a voltage source. 0 volt voltage source is a wire. So we would imagine shorting that out. The 2 ohm, 3 ohm is in parallel, right? We have 6 over 5, and then the 6 over 5 ohms plus 8 ohms, right? It's kind of looking exactly like what we have right here. Gives us our Thevenin. So that's another way we could have found our Thevenin if that's all we needed. But going through this whole process allows us to find the full Thevenin and Norton equivalents. So that's all for that. Do I have any questions? No? All right. So, and if you do have any questions, feel free to send me an email, send me a message, talk to me in class. But yeah, I really hope this helped, and I will hopefully be, I will be helping out with some differential equations here soon, especially with capacitors and inductors. That really starts coming up and can be difficult if it's a course you haven't dealt with in a little while. So awesome. Have a great day.